Okay, so our next video is going to be about integral domains. So what makes an integral domain different from a ring in general? One thing is that it has to be commutative and with unity. So that's going to be common for most of the rings we deal with. The main thing is it doesn't have things called zero divisors. And so a zero divisor is an element A, which isn't zero, but such that A times B is zero for some other element B that also isn't zero, right? So usually you have that AB equals zero implies A equals zero or B equals zero. But this fails unless R is an integral domain. So that's the main thing, right? And we use this all the time, like for factoring polynomials and stuff. So a good example to keep in mind, we've looked at Z12 above, so if we look at Z6, just to make it a little bit simpler, we have, for example, that 2 times 3, now clearly 2 is not 0, and 3 is not 0 in Z6, right? But this is 6, and that is 0 mod 6. Right, so Z6 is not an integral domain, right? On the other hand, above, we showed that 2 times Z6, right? So the elements just in 0 to 4, this is an integral domain, strangely enough. And in this integral domain, in fact, everything has an inverse, and 4 is the identity element. It's sort of an interesting little funny example to keep in mind. But anyway, that's the definition. Now we're going to be doing important stuff with integral domains from now on. So a lot of the times we're doing stuff with rings, we'll be doing stuff with integral domains. One important thing is this. So if, and I guess I don't have this in the notes. I need to add this to the notes. Let me add it. Okay, so you can see here I added a thing. So if A is in UR, the set of units, right? So things that are invertible, right? Then A is not a zero divisor. This is zero divisor. I'm just going to abbreviate that, zero div. I guess we don't have an abbreviation for the set of zero divisors. Let's see, the main thing here, let's see, so we have AB equals 1, right? But now if A had an inverse, right, then we have A inverse A. I'm going to say, suppose it's a zero divisor, right? So if AB equals 0, then A inverse AB equals 0. But this would imply that 1B equals 0. That would imply that B equals 0, right? So we're not looking at a case with zero divisors. So in particular, if we have an inverse, it cannot be a zero divisor. Good. Okay, maybe it's kind of silly. In some sense, I said that the thing that you're multiplying by has to be 0, but that actually takes care of the thing, because to be a zero divisor, both of these have to be non-zero. Good, okay. Here's an important thing. Remember we said that we probably won't be doing much with products in the case of integral domains, right? And so here's the reason, right? So if we have S and T rings, then, right, then S cross T, or S times T, or S plus T, it depends on what notation you want to use. Here the two groups we're putting together are additive, so maybe I should use the additive notation. Has zero divisors. And so this is really easy. In fact, there's lots of them, right? So S together with 0t, right, times 0s together with t, right? So this is kind of anything in the copy of S, which I tend to call S hat. This is anything in the copy of T, which I tend to call T hat, right, is actually equal to 0, right? And this is the 0 of S cross T, or S times T. All right, so there's lots and lots of 0 divisors in sums or products of integral domains. So we don't have any sort of nice theory about the product of integral domains being integral domain, or integral domains breaking into products of integral domains, or anything like that, right? Because it just doesn't happen, right? I mean, it is possible that these are both integral domains, and the, well, never mind. No, it's not possible because we have 0 divisors. Okay, let's see, what else did I have here? It's that. Okay, yeah, polynomials over an integral domain. So yeah, so this is going to be really, really important for some of the stuff we do. So if R is an integral domain, then Rx is also an integral domain. Now we're going to have lots of theorems like this where R is a something, then Rx is a something. And then sometimes we'll have that if R is a something, not necessarily the case, Rx is a something. And these, besides being important to know, they're good true false questions, right? So is an integral domain. So how do we show this? So suppose F and G are in Rx. And this is actually really easy, right? And so let's say F is equal to an x to the n plus, and then some stuff. We don't really care what the stuff is even. And g of x is equal to, by the way, I can leave off the x. I mean, we know these are polynomials. So we'll say this is bm x to the m plus some stuff, right? And then fg is going to be, well, it's going to be anbm x to the n plus m plus, and then all this stuff out here, right? Now, what is this stuff going to be? Well, it's going to be this stuff times that, this stuff times that, then those two stuffs times each other, right? But that doesn't matter. The leading term is that, right? And since a n, b n does not equal 0 because a n was not 0 and b n was not 0, right? Because we're in an integral domain, right, then we know that this term is not 0. And so, in fact, we know the degree of f times g is the degree of f plus the degree of g, right, which is something that failed in general earlier, right? So anyway, these are, but I mean, in particular, these can't be 0 divisors, right? These two things cannot give me 0 as a product. By the way, 0 here means 0 as the 0 polynomial, right? Good. Okay, so given that, right, we can even keep going, right? So once we add one variable, we can add another, right, etc. Right. So if I look at polynomials over n variables, this is still an integral domain. Okay. We won't do much with that, but it turns out to be really important if you continue studying algebra. Let's see. One other important thing in this little section is if we have p of x equal to x minus a1 through x minus a n. Now we're gonna, or a k is what I have in the notes. We're gonna generalize this a bunch in the future. Then what we see here is we see that p of a equals 0 if and only if a equals ai for some I. So this is something you use when you're trying to break polynomials into pieces, right? We saw earlier that this kind of thing doesn't happen in Z12x, but Z12x is not. Z12 is not an integral domain, so Z12x is not an integral domain. Why is this true? Well, if we plug in an a in here, right, then we get a minus a1 times etc. a minus ak. The only way that can be 0 is if one of those terms is 0, but that means exactly that this has to happen, right? So So there's only one way to take a polynomial and factor it into linear factors where the leading term of each factor is monic. You know, the coefficient there is 1. Again, when we get to fields, we'll be able to do a lot more than this, because then we can divide and we can make them have this form, right? In general, if we're in an integral domain, we can't factor things necessarily into this form. Okay, so that's important. And then just to revisit character real quick, right? The only way, yeah, so if R is an integral domain, all right, and char R, the character of R is in, you know, less than, well, okay, I guess 0, so not 0, right? That's what I want to say here, not 0, right? Then in fact, we know that a to the, well, we know that the order of a for every a that's not 0 is actually equal to n, right? I guess what we know here is this. We know that from the earlier stuff, we know that the order of a divides n, right? But once we know the order of a divides n, then we would have, you know, this thing would factor into like a to the, I want to do this. It would factor in just oops, pause for a second. Okay, so yeah, I had to pause there for a second and think. So let's forget the argument I was about to do. We just have this, right? We know the character was the least n, such that 1 plus 1 plus 1 plus 1 equals, you know, n many copies of 1 equals 0, right? That was the definition. If we had a plus, no, a is not 0. Suppose a is not 0, right? Suppose we could add a many copies of, sorry, m many copies of a with some m less than n, right, and get 0, right? Then what we would have here is we could factor out an a and get this, right? And there would just be m many copies of 1. This would be equal to 0. But now, since we're in an integral domain, right, one of these would have to be 0, and since we're assuming a is not 0, right, the only option would be that this is equal to 0, right? And that would mean that you know, m is equal to n. I mean, so m couldn't be less than n, right? It could be n, could be a multiple of n, but couldn't be less than n. All right, so that'd be a contradiction. Okay, so yeah, so in an integral domain, everything has order n. Sorry, this is the wrong. This is additive order, right? So n a, right, equals 0 for all a, and ma does not equal 0 for all a not equal to 0. And sorry, gotta write everything less than n, right? So if we add a to itself n many times, we get 0. If we add a to itself less than n many times, we do not get 0, right? So the additive order of a is equal to n for all a inside of the integral domain. Okay, let's see. So the next little example here is Gaussian integers. These turn out to be really, really important examples of things, right? In fact, not only just, so Gaussian integers are things of the form like this. So a plus bi, right? Or a and b are in z, right? Or it doesn't have to be z, it could be zp. And I'll have some separate notes just about this. You could say a whole bunch of stuff about Gaussian integers where a and b are in ZP, right? So both of those things, right? And in fact, this notation is quite general. So we have like QI, right? Is a set of A plus B I, where A and B are in Q, right? And similarly, we have RI, right? We have all these guys, right? And RI is also called C, right? The complex numbers. right? So we have lots and lots of examples like this, but I'm primarily interested in these two. These are fields, right? And so when we have fields there, things are a little bit nicer. These are sometimes fields. So when P is so when is this an integral domain? Well, it's only an integral domain when this is a field, right? So these finite field cases, right? Now this is never a field, right? So this is the case that's really different because it's not a field, right? So but still these two cases are kind of new. Let's see. So I want to say that these are integral domains, okay? And actually the same proof works in both cases. So, I mean, again, the fact that P is prime, what P is prime is giving me in this case, right, is that the ZP is a field. That's the thing that it's giving me. For part of the argument, I'm just going to use that P is odd, right? So let's see that there's no zero divisors. So to see there's no zero divisors, we have this kind of argument. So suppose, so here's a thing to note, right? So if I have W and Z, sorry, if I have W and Z, element of one of these things, Zi or Zpi, so I'm going to use the same argument for both. All right, then here's the thing we have W squared, the length of the magnitude of W, or W squared, right, is going to be like A squared plus B squared I, where W equals A plus BI, okay? And now notice if we took the square root of this, we might not be getting something in the right, Z or ZP or something like that. We have to be looking at the squares here, right? Let me make sure that I is visible there. This is also the same as W times W bar, right? So that's something you might remember from complex analysis. The algebra works out exactly the same. Okay, and an important fact is that W times Z is equal to WZ. Okay, it may be even more important for us, and I'm not saying anything different, just that this is kind of how we use it. W squared Z squared is equal to WZ squared. Right, so those are basic facts from like complex analysis, right? Okay, so here, right, so I want to say suppose WZ equals 0, right? I'm trying to show there's no, in those two cases, right? So again, the cases I'm interested in, ZPI and ZI, where P is a prime, right? P is an odd prime, right? Z2 is maybe a little bit different. So I want to show there's no zero divisor. So suppose WZ is equal to 0, right? Well, I can take the length squared. If this is equal to 0, this is also equal to 0, right? But this is equal to W squared and then Z squared, right? So what do we get here? Now these things are just in, in Z or ZP, depending on which one of the two cases we're in, right? So that tells me that W squared is equal to 0, or, Z squared is equal to 0. Okay, well, let's suppose we're in the case where W squared is equal to 0. So this is actually A squared plus B squared, where W equals A plus BI. All right, we're saying that that is equal to 0, right? And now we want to consider how that can happen, right? So how could it be the case that this is equal to 0, or it can be the case if A squared plus, well, okay, so first of all, in Z, this can't happen. Unless A equals B equals 0. So in other words, unless W is 0, right? So that's what we wanted to see, right? ZP is a little bit more interesting. So in ZP, what we would have to have happen is we'd have to have A squared plus B squared is equal to, basically equal to P, right? Maybe a multiple of P, but basically you can get it to just equal P, right? And now remember, I'm assuming P is odd. Okay. So let's see, maybe I said something a little bit wrong. I want to say, yeah, I got it. I better backtrack a little bit. I have it right in the notes. I want to say that ZPI is an integral domain IFF. P does not equal 1 mod 4, right? So that looks a little bit funny. This looks a little bit number theoretic-ish, right? And in fact, what we're playing with here is something that was studied by Fermat, so back when he was doing number theory. Maybe something you studied in 525, right? So the point is this: suppose P is odd. So I'm actually so now I'm just going to concentrate on the P is odd part. We don't even need prime for what I'm about to do. Suppose P is odd, then one of two things happens. Either P equals 1. Okay, so I did take a little break because I'm coming back. So if P is odd, then either P equals 1 mod 4 or P equals 3 mod 4, right? Those are the only two options if P is odd. That's easy to check. Okay. What I want to see is that if P equals A squared plus B squared, right? Then it must be the case that P equals 1 mod 4, right? So this is actually the easy direction. This direction, P equals 1 mod 4, okay, plus P prime, actually implies P equals A squared plus B squared. Much more interesting, right? This part is due to Fermat. Right? The other part's kind of simple, so it's too easy to say it's due to Fermat. So the point is this, right? If P is if P is odd, right? Then we know that one of A and B has to be even, one of A and B has to be odd in order for that to be true, right? So we may as well assume that A is even, so A could be 2A prime, right? B could be 2B prime plus 1, right? Because it's odd, right? And then A squared plus B squared, if you just work it out, right, is going to be 4A prime squared plus 4B prime squared plus 4B prime plus 1, right? And all of this, right, is equal to 0 mod 4, right? So clearly what we get is we get that A squared plus B squared is equal to 1 mod 4. This is assuming that A squared plus B squared is odd. That's all we're assuming here, right? So we're in that case, right? So in the case that P is odd, and now we're going to go back and use the fact that P is prime, so the ZP is actually an integral domain, right? Then we have that, so ZPI is an integral domain. As long as P is prime and P equals 1 mod 4, right? Or you could, say, and I do this in the notes, say P not equal to 3 mod 4, right? Oh, sorry. Yeah, sorry, I'm getting myself a little bit confused. So if this holds, right, then it's not the case that we have an integral domain. So sorry, I need to say this correctly. I need to say this is an integral domain if and only if P is prime and P does not equal to 1 mod 4. Because I want this to not happen. I want it to not be the case. So we need to avoid A squared plus B squared equals P, right? That would be the problem case. Okay, so in the notes I have it written correctly, and I even have this little proof in the notes, right? So that's right here. It's a good thing to think about. All this stuff is good to think about. Also, some links to a really great proof of Fermat's theorem, and then some information about this thing. One thing I forgot to put in these notes. So the next thing is fields, and then I want to say one more thing that I don't have in the notes. Actually, I'm gonna pause it again and add it.